Standard multi-agent routing networks and TCP/IP systems share a structural limitation. They rely on flat Euclidean addressing architectures. They process data through two-dimensional meshes and Cartesian coordinate grids. The direct mathematical consequence of this flat geometry is that routing updates follow a linear scaling law. As the network capacity, or K budget, expands, the computational footprint grows exactly at a rate of k to the power of 1.0. Under high load, this linear scaling triggers hardware failure. The static partitioning of memory addresses causes latency spikes, buffer overflows, and state-locked memory utilization that surges to 92%. The R4 prime router resolves these vulnerabilities by achieving a sublinear computational footprint. This chart plots standard linear k to the power of 1.0 growth against the router's performance. The system achieves a scaling metric of k to the power of 0.572. At a dense routing budget of 5,000, this yields a 2.6 to 2.8 times compute reduction compared to a standard linear model. The R4 prime router accomplishes this by replacing standard deep learning gating networks with a deterministic topological framework. Managing terabit-scale multi-agent coordination on local hardware like the Apple M1 requires bypassing traditional memory allocation bottlenecks. This hardware bypass is achieved by replacing adaptive gradient descent-driven gating matrices with fixed geometric mappings. The exact mechanism driving this geometry is the Hopf Angular Routing Protocol, or HAR. To understand how HAR executes this computational reduction, we have to deconstruct the internal geometry of token embeddings and the four-step mathematical projection used to route them. The deduction begins with the state vectors of modern language models. We need to look at how token embeddings physically occupy space. This is a visualization of token representations when they are L2 normalized. They are projected directly onto a unit hypersphere. The primary geometric fact of this space is that these embeddings are angularly non-uniform. They cluster into specific preferred angular regions rather than distributing evenly. Standard compression methodologies, like TurboQuant, destroy this spherical structure. They apply random orthogonal rotations to force near-independent scalar components for quantization. The HAR protocol makes the opposite engineering choice. It exploits this inherent structural bias. By projecting a fixed sector map over this sphere, semantically similar tokens are captured into specific regions, leaving the majority of other sectors entirely empty. By utilizing this native angular sparsity, the system restricts the hardware's workload to the specific paths containing active semantic data. Standard adaptive k-means clustering algorithms fail to accurately map this non-uniformity because they rely on flat space calculations. Euclidean centroids miss the internal fiber geometry of an S3 manifold. The data exists on a curved geometry that requires a topological projection down to an S2 base space and an S1 fiber circle. This continuous manifold then maps to a physical hardware substrate through a discrete hex-hive modulo 6 topology. The physical node interfaces are mapped exclusively onto coordinates defined by the distribution of prime numbers. Parallel channels are established at distinct indices belonging to the same residue class modulo 6. Because these addresses follow the arithmetic distance of prime coordinates, the parallel routing paths cannot naturally intersect. Mapping a continuous hypersphere onto these discrete prime indices eliminates coordinate drift. The packets curve past each other in high-dimensional space, avoiding Cartesian collisions. To translate this into physical hardware operations, the router executes a rigorous four-step algorithm on any L2 normalized input vector. Step 1 projects the normalized input into a fixed four-dimensional Hopf subspace, extracting four absolute base coordinates, A, B, C, and D. Step 2 computes the local Hopf base coordinates to isolate the coarse global address, leaving the internal structure defined solely by relative phase offsets, represented by the fiber mean phase, alpha. Hardware proxy logs confirm that this raw fiber phase is the primary mechanism of the architecture, delivering 66% of the routing concentration. Step 3 applies a Levi-Civita phase transport correction. This calculates the phase evolution of the signal during its rotation. Upon closing the routing loop, the accumulated geometric phase shift, known as an holonomy, represents the literal friction or computational cost of the route across the curved space. Finally, step 4 takes this transport calculation and assigns the vector to a final discrete sector across the routing budget K. By running incoming data through this fixed, deterministic 4-step chart, the network executes precision routing through angular geometry, removing the need for learned parameters. Operating mathematically in curved space still requires confronting the write speed limits of local memory caches. The architecture solves this by discarding static RAM addressing in favor of phase-based continuous buffering. Memory addresses become oscillating phases within stable limit cycles. When a packet burst hits the router, the system state undergoes a supercritical Hopf bifurcation. This bifurcation allows the router to dynamically buffer incoming coordinate streams within the continuous phase of the computational cycle itself. This predictive buffer algorithm uses the manifold's curvature to place required local vectors in the cache before the CPU even requests them. By ensuring a 97.4% cache hit ratio, the system suppresses synchronization overhead to 0.15 milliseconds, bypassing the traditional request and wait cycles of standard RAM. This table displays routing budget versus effective footprint, proving the K to the 0.572 efficiency limit. At a budget of 1,000, standard linear scaling demands 1,000 cells. The AAR protocol requires only 392.1, a 2.55 times compute reduction. Reaching 5,000, the ratio locks in at 2.60. The quantitative data confirms the mechanism's behavior. As the network capacity expands, the Hopf coordinate mechanism occupies a decreasing fraction of available topological cells. These hardware savings were validated against the null result during mixture of experts training. The research proved forcing rigid mappings onto adaptive layers is functionally inefficient. Dynamic subnetworks will fluidly absorb and reorganize topological impositions. Transitioning the addressing layer to the discrete hex-hive topology natively filters semantic paths, establishing a deterministic, collision-free coordination substrate at the hardware level. High-dimensional capabilities like routing and selection are not separate software additions. They are emergent properties that arise directly from the underlying geometric and physical dynamics of the manifold itself.